Good afternoon and welcome to a new exciting AI Factories for Telco Edge. I am Alfonso Carrillo Espiazu, Principal Edge Solutions Architect at OpenNebula Systems. And today we'll look at how to package and operate a hyperconverged edge cloud to enable AI inference and a fully virtualized 5G core. As you may well know, this work builds on what we presented at the Mobile World Congress in 2025 and at our previous webinar on AI on 5G O-RAN automated deployment. Today, we bring those ideas down to earth with a practical AI plus 5G core demo and on real infrastructure. We aim to show how OpenNebula can be deployed easily across environments and architectures, following a hyper-converged approach, storage pool, virtualized resources, and the management plane live on the storage, live in some high availability host. We use our own one deploy, our official Ansible playbooks, and we do this in a scaleway cloud, just as you will do in last mile edge sites. You will see how we leverage NVIDIA GPUs for accelerated compute inside VMs, now simpler with the latest one deploy playbook, and how OpenNebula's virtualization clusters support cutting-edge apps from LLM training and inference to deploying a 5G standalone core. The targeted scenario. Okay, well, we have 3 bare metal servers on a scaleway, a private network, and a public gateway. With one deploy, we'll automatically bring up an OpenNebula front end in high availability. The hyperconverged Ceph cluster turns local disk into a resilient storage pool and configures KVM and all nodes for VMs. On one server, we enable GPU pass-through to assign the GPU directly to the VM. Furthermore, the magic really lives in the Ansible inventory. We describe hardware, networks, and cloud parameters. One deploy builds the OpenNebula control plane, prepares Ceph, registers KVM hypervisors, and sets up the GPU pass-through. The outcome is a high availability cloud ready for appliances and reproducible pipelines. The same recipe, different sites. AI plus 5G core showcase application and 5G network simulation. With the infrastructure ready, we run 2 representative workloads. AI, deploy the OpenNebula Array appliance with GPU pass-through to run an LLM. And the 5G core stands up as a complete 5G standalone core using Open5GS and connected to a UVEG node simulator using UrenaSim. So you'll see all this in the further demo that we'll have. Through the demo, as will be explained further down, but we will use a one deploy inventory, high availability control plane, a distributed storage. You could see it clearly on as we build it. KVM hypervisors, GPU pass-through, which is quite an important need on the hardware to really have the VMs and the AI working completely. And this is something that we have achieved, making it possible to have share the EPU, providing multi-tenancy on the GPUs. And then the appliance rollout will deploy the array plus the LLM and the Open5GS, and you'll see all that on the screen as well. One Edge 5G and an innovation framework. Excuse me, sorry about that. One Edge 5G is the project that has provided us all the possibilities of building this, and it provides intelligence and automation for operating distributed edge systems on advanced 5G infrastructure. It's funded by Spain's Ministry of Digital Transformation and the Civil Service, and they're a project in the UNICO R&D 6G program. With that, and not further more to say, I'll pass the presentation to Álvaro Curto from Telefónica Innovación Digital, who will go through the details of what we are going to show you today, and also do the demo at the end of the presentation.
Okay, thank you, Alfonso. So, my name is Álvaro Curto from Telefónica Innovación Digital. I work as a mix between a DevOps engineer, a networks engineer, and an infrastructure engineer for several networks-related projects. My team in Telefónica has used OpenNebula for over 3 years now, I believe. And we've been using OpenNebula to satisfy all of our virtualization needs over multiple environments and over 40 servers. Most of our environments are running using an architecture based on the one that we will use on this demo. And for that and for other reasons, that's why OpenNebula has trusted us to conduct this webinar with them. This is not the first collaboration between OpenNebula and Telefónica, and well, hopefully not the last. So I would like to begin with discussing the environment where the demo will take place. The whole setup will try to resemble the infrastructure expected to be found at an AI factory, an edge location, a 5G MEC, you name it. So to simulate that, we will use a bunch of bare metal servers from a cloud provider, and our cloud provider of choice will be Scaleway. So why Scaleway? There are a few reasons. One of them is the current European context, with the European Commission launching tenders focused on cloud sovereignty, and besides, to force us to depend less on the traditional American hyperscaler clouds. Scaleway rises up as one of the most prominent and mature cloud providers based on the European Union. Not only that, its broad catalog of services include bare metal as a service with several types of instances, including servers with GPUs that we will use to pass through to our VMs to run hardware-accelerated workloads. Now, in order to reduce the amount of servers required, we will follow a hyper-convergent infrastructure architecture, or HCI for simplicity. This allows us to combine the storage, computing, and networking layer of our cloud into the same 3 servers without compromising performance. We also want our environment to be highly available in case one of our servers fails, and that's why we use 3 servers at minimum. This will be connected with a private network, and we'll have a public gateway for the VM's internet access. So this is the HCI architecture we will be using. You can see the 3 bare metal servers, all contained within the same virtual private cloud. They are connected using a virtual network, and there is a public gateway serving as the default gateway for the VMs we will create. Using the nomenclature of Scaleway, we can differentiate between 2 kinds of servers. The first 2 are 2 elastic metal berylliums. They come with a fair enough amount of computing resources and 10 gigabits per second of bandwidth for the private networking. And the last one is more powerful. It's a titanium. It comes with much greater resources. It's more expensive, but most importantly, it comes with 2 NVIDIA L40S GPUs. These servers will form at the same time a Ceph storage cluster and an OpenNebula cluster. OpenNebula will use Ceph as its storage backend. It's a pool of block storage. OpenNebula will be installed in a high availability manner with 3 frontends running each on their own virtual machine on the same hypervisor nodes. It's worth noting that this setup is for demonstration purposes, and that real production deployments should aim to use 3 servers of the same kind, not one really different to the other 2, like we are doing here. The only mandatory requisite in your environments or in your edge locations, whatever, is to have a wide enough internal connectivity between the hosts with 10 gigabits or more. That is because one of the main bottlenecks of this setup is the Ceph storage cluster. It will consume most of the bandwidth. If there isn't enough, it can throttle the I/O performance of all of the workflows or workloads. So that's all from the architecture side. But how do we achieve this setup in an easy and streamlined way? The easiest way is using OneDeploy. OneDeploy is basically a collection of Ansible playbooks and roles to deploy and configure an OpenNebula cloud from start to finish. It will take care of most, if not all, of the pre-requirements and will cover all the necessary phases. It utilizes Ansible, which, as you might know, is the most popular configuration as code tool in the industry, and for a good reason. Its syntax is easy to write and to understand. It has an impressive amount of community plugins and integrations, and it generates idempotent results. This allows to rerun the same scripts with slightly different values, achieving predictable results. It ensures that a specific configuration is successfully applied in a repeatable and scalable manner. OneDeploy playbooks can be parameterized like any other Ansible playbook. That is through variables and the inventory file we will use. In Ansible, a single inventory file can describe the different targets for our configuration and the variables they will use to achieve what we are looking for. We created a specific inventory file for the HCI architecture, and we hope we can upload it to the upstream OneDeploy repository in the following days. So yeah, OneDeploy has existed for a while now, but the only one thing we couldn't achieve with the existing playbooks is to configure and enable PCI pass-through. This is one of the tasks that Telefonica, in collaboration with OpenNebula, has recently developed and hopes to merge it to the main branch. We have created a new playbook and a new role to perform the required steps on both the KVM nodes and the front-end nodes. So for this demo, right, once we have access to the bare metal servers and we made sure that their networking is okay, OneDeploy is used to set up everything else end to end. The tasks it does can be resumed into these 4 points. First, it configures the bare metal servers as KVM hosts, as OpenNebula calls them, enabling virtualization to happen on them. Then we deploy the Ceph storage cluster over the hosts using one of their spare disks. Each host acts at the same time as Ceph monitor, a Ceph manager, and a object storage daemon to manage the disks. And this provides us with a single resilient pool of shared storage. Then we proceed by building the control plane of OpenNebula. As previously explained, we first raise up one VM in each one of the servers. Then we install the OpenNebula packages on those VMs, and then we configure the high availability frontend. And well, the last step is what we have recently developed. It configures the PCI pass-through for NVIDIA GPUs. This playbook, it's a lengthy process involving several reboots, so we believe it's not fit to be shown in the final demo, but it's a required step. And once everything is already set up, we can test our new environment with some applications. We are going to start by deploying a lightweight AI application that can take advantage of GPU acceleration. And then we are going to run a quick simulation of a 5G standalone mobile network, where all the components, the 5G core, the UNOV, and the user equipment will be virtualized. The first of these experiments, the AI application, will use the Ray appliance from OpenNebula's official marketplace. Ray is basically an open source framework designed for distributed computing and machine learning workloads, particularly useful when scaling AI applications across multiple nodes or hardware resources. OpenNebula's Ray appliance consists of a single VM offering a streamlined solution to build and serve end-to-end AI applications. Among their options, it lets the user to choose between a selection of pre-trained models from the Hugging Face Transformers library, which allows us to run an LLM without needing to train anything from scratch. We are going to instance Array VM with its own dedicated GPU to efficiently run an LLM with full hardware acceleration. And the process to achieve this is quite straightforward. Once the VM is up and running, we only need to install the latest NVIDIA drivers to that GPU model, reboot the VM, and the LLM should be up. And the last test, we'll try to create a 5G mobile network simulation by virtualizing first the network functions of a 5G standalone core, and then virtualizing the RAN and UEs. For the 5G core, we will use Open5Gs, and for the RAN and the UE, we will use RANSIM. Both they come in their own appliances that can be deployed independently, and these appliances are available as of right now in OpenNebula's community marketplace. You might need to configure that marketplace in your environments first to appear on your OpenNebula available appliances. So one last note, for production workloads, Open5Gs or any virtual 5G core can be deployed in more scalable formats than a single VM. For instance, we used to deploy it in Kubernetes clusters running on OpenNebula using 1KE. And for Open RAN solutions, you can check out a previous webinar called One Demand Private 5G with OpenVRAN and OpenNebula. Well, that's all for the description of the demo. As you might imagine, due to the nature of what we just have said, we won't be able to
Welcome to
a
the
live demo.
Emulated AI Factory.
It's a lengthy process with many relevant parts like the one deploy usage, where the demo would be only watching logs. So we reduced the demo to a 15 minutes video edited and much more digestible for the audience, we believe. Okay, so here it goes.
Factories for Telco Edge end-to-end AI RAN automation with OpenNebula Screencast. In this demonstration, we are going to build a complete hyper-converged OpenNebula cloud on top of the Scaleways bare metal servers. Our goal is to use the private cloud to run two workloads, a GPU-accelerated AI application and a full 5G mobile network simulation. The content of the following demo is summarized here. First, we lay the foundation by provisioning 3 bare metal servers on Scaleway, connecting them with a private network and a public gateway for internet access. Next, we are going to use the OneDeploy automation tool to install a high-availability OpenNebula environment, a distributed Ceph storage cluster, and to configure the NVIDIA GPU pass-through. With our cloud up and running, we will deploy our first workload, a large language model using the OpenNebula Ray appliance, providing it with a direct access to a physical GPU for maximum performance. Finally, we'll create a complete 5G network simulation by deploying and connecting the Open5GS and URANSIM appliances right inside our cloud. This demonstration was developed in collaboration with Telefonica. Let's take a quick look at the architecture. Our 3 servers are connected via the administration network for all our internal traffic. Each server will also host a virtual machine for the OpenNebula frontend, configured in the high availability setup. A virtual IP is going to float between these frontends should the failover happen, ensuring the OpenNebula services are always accessible. The bare metal servers are also act as our KVM hypervisors, running the application virtual machines. To provide internet access to these virtual machines without exposing them directly, we'll use Scaleway Public Gateway. If we want to expose a specific service, we can easily assign a flexible public IP to any virtual machine. The hardware for this demo consists of two standard beryllium servers and one powerful titanium server, which comes equipped with two NVIDIA L40S GPUs. We'll use OpenNebula to pass these GPUs directly to our AI virtual machines. With that covered, let's begin the setup. The first step in our setup is to access bare metal instances and launch an Elastic Metal server. We will use the Paris 2 availability zone and the hourly billing. Choose a Beryllium instance, specifically the one with 10 gigs of private bandwidth. I will select a Linux distribution and provide a different partitioning for the disks. Instead of using RAID, I will be leaving a spare disk that we'll be using for Ceph later. Now add some custom tags, your secure shell key, and, very important, select Enable the private networking feature before creating the server. Repeat these steps to create the second Beryllium instance. Now we will need to create a third Elastic Metal server with a GPU. These are called titanium instances, and we will use the simplest one. The rest of the process is pretty much the same. After waiting for a while, we can see that all three servers are fully deployed and online. Currently we can reach them via their public IPs, but we want to create a private subnet between them. Enter one of the servers and choose to attach it to a private network. We don't have one yet, so we will create one in our virtual private cloud and then attach all three servers to it. If I will navigate to the VPC settings, I can see the private network and the IPs are assigned to the servers with their own VLAN. Now when we have a private IP assigned to each server, we can configure it. If you examine the current network configuration on a server, you'll see that it only has DHCP configured for the first network interface. Therefore, we need to create a new configuration for our private IP addresses. It's essential to use the new virtual interface tagged with the correct VLAN. While a standard interface would work, for the future OpenNebula use, it's better to use a bridge attached to the physical Ethernet port. I will create one now. After applying the configuration, we can see that the new IP address is active, and I can ping the other servers that I have already configured this way. Now that we have internal connectivity, we still have a few steps left. This private network is where our future virtual machines will get their IPs, but right now the network is totally isolated and doesn't have the internet connectivity. To solve that, we'll need to create a public gateway. We are going to create one in the same availability zone. The cheapest one should be fine. Once it is allocated, we have to attach this public gateway to our private network. The final step is to reserve a few IP addresses for the resources we plan to create. We should reserve an IP address for each of the OpenNebula frontends and one for the virtual IP usage. Any available IP is okay. Repeat the process a few times. With our Scalable infrastructure ready, we can now deploy the entire OpenNebula cloud using one deploy, which is a robust set of Ansible automation scripts. We will exclude the execution steps from this demo and provide a summary of the deployment and configuration steps. The process starts with filling the inventory file. This file acts as a blueprint for our entire cloud. Here we are going to provide all the details from our Scaleway setup, for example, IP addresses, and define our target architecture, specifying that we want a high availability control plane and a hyper-converged Ceph cluster for storage. First, the script builds the control plane. It automatically creates the dedicated virtual machines on our bare metal hosts that will form the high availability cluster for the OpenNebula frontend. Next, it is going to deploy the distributed storage. The automation sets up our hyper-converged Ceph cluster, transforming the spare local disks on each server into a single resilient storage pool for all our virtual machines and images. Once storage is ready, the script configures the hypervisors. It installs all the necessary software on our bare metal servers and enrolls them as the KVM nodes within the OpenNebula cloud, making them ready to host the virtual machine workloads. Finally, the automation enables the GPU pass-through. A specialized task runs only on our Titanium server, reconfiguring its kernel and drivers. The critical step helps the powerful NVIDIA GPUs to be directly assigned to our virtual machines, which is essential for our AI workloads. Now that the described OpenNebula deployment automation has been executed, let's access the UI and verify the deployment. We can see that OpenNebula recognized the three hosts, and this one has the GPU pass-through configured. Now we will deploy AI workloads in our OpenNebula environment. To achieve this, we will utilize the Ray appliance, which is available in the public OpenNebula marketplace. We need to download it and select the data store. We will instantiate a virtual machine using this template and allocate more resources. I will use a different model with Ray framework. Next, we need to give it a network interface. I'll be using the default virtual network that the One Deploy tool provided us. Most importantly, I will assign one of the GPUs from the third host. The scheduler should be aware of the PCI device location and assign this virtual machine directly to the appropriate host. Now we will give it some time until it finishes deploying. Our virtual machine should be already working and exposing the LLM. For now, we must manually log into the VM and install the latest NVIDIA drivers. I've already performed the necessary steps just a moment ago. Now, after rebooting the virtual machine, we should verify that the LLM is utilizing the GPU. It's working already. The Ray appliance comes with a web UI to test the LLM, so we should try it. The web service runs on the port 5000. Accessing the service, we can initiate a chat with the LLM and observe that it provides a generated response as expected. Lastly, we will deploy a 5G application into our environment. For this, we will need some appliances that are available in the OpenNebula community marketplace. Those are Open5GS and URN-SIM, which are emulators of mobile devices and radio access networks. First, you will need to create a marketplace entry to import them. Before we deploy the 5G core and the RAN, we'll first create another virtual network. I will use the VXLAN type on top of our private bridge with the automatic VLAN ID. I'll set the address range and lower the default MTU because of the VXLAN headers. We will run this virtual machine with host pass-through of the CPU. Now we can deploy our 5G core. I'll give it a name and increase default resources. Before filling in the inputs, I will increase the default storage size to 10 gigabytes. And will fill in the network information. I will use the default virtual network for secure shell access and attach a second network interface using our new virtual network, specifying a specific IP address. Now I can go back and input that IP for N2 and 3 interfaces. The remaining parameters can be left on their defaults. Before using this 5G core, we need to take two steps. One, we will need to change the AMF configuration. That is to add an SNSS AI. Now restart the Open5GS service. The last step is to create a network slice for our radio access network. We can do that in the web UI. We'll create a subscriber, fill in the MCC and MNC, and complete the key until it has 15 characters. The rest looks okay. SST and SD will be set to 1 and 11111 respectively, and the APN is set to Internet. We will now create a VM for the URN SIM. We will follow the same steps as before: more resources, and the user inputs should match the configuration of the Open5GS. The AMF IP address was set to 10.0.0.2. The MCC was 999. MNC is 70. The SST is 1, which we have just configured in the Open5GS VM. For now, we do not need to configure the virtual router and the core subnet, so we will fill them with the placeholder values. For the networking, we will use one NIC for the secure shell access and the second NIC for the 5G traffic. Now, as the VM finishes deployment and booting, we are ready to verify the connectivity. If we go to the URN SIM VM, it was already attached to the 5G core and is using it to forward traffic. So if we ping Google utilizing the interface, we can see that the RAN simulation has public internet access. The logs of the UE and the GNodeB are also available to verify the correct operation. That concludes our demonstration. We were able to run the AI workload using the GPU capabilities and a functional 5G mobile network over the OpenNebula environment running on a bare metal server in the Scaleway cloud. This screencast was produced in the scope of the One Edge 5G project. Thank you for watching and see you in the next screencast.
So that was all for the demo. I hope it was useful for you. And we will conclude this webinar with a section of questions and answers along Ballast and Antonio. Alfonso again.
Yeah, hello. So we didn't receive any live questions yet, but you still have a few moments to send us. And in the meantime, we can answer one of the questions which we have received in the registration form. So I will read it out. I think it's a question to Alfonso. So the question says that how can telcos practically integrate AI inference workloads with 5G RAN functions at the edge without over-provisioning GPUs or compromising on latency? Do you have any advice on this, Alfonso? You are mute yet, so you have to unmute yourself first.
Great. No, it's a very nice question. There we can take advantage of OpenNebula's native multi-tenancy possibilities or functionality. We have already proven this working on when we did a 5G neutral hosting, where we assign resources to each one of the MVNOs that was being provisioned and providing services without interfering with each other on the assignment of the physical infrastructure. We took it one step further, and we used only one single socket of the server to run both MVNOs in the with separate 5G ORAN appliances on them. So, and there was no interference. We could assign resources. So this is the same approach we will use to ensure that the 5G resource requirement don't overstep on the AI inference compute requirements, and vice versa. So we are confident that we will achieve no loss or increment on latency, and that the GPUs will be, and that the AI inference will be working at full capacity as well. I hope this answers the question.
Yeah, I think so. Thank you. And I don't see more questions, so from the audience either for now. So yes, I think we can close the webinar here. Thanks a lot for attending us, and if you have any follow-up questions relating to this topic that we have presented, feel free to reach out to us.
Thank you very much.